Welcome to my video. Now, in this video, we're gonna learn more, or we're gonna do more questions on thermodynamics. Without wasting any time, I'm not gonna dwell on the basic, but it's all about solving the questions. So, without wasting any time, let us go through the questions. So, I'm gonna start with the first question, where it reads as follows. We have the statement and the question at the same time. They say to us, determine the work done for each process in the polyprotic cycle. Process in the figure below considering the given data. So we are given the CV, it's 735 joules per kilogram Kelvin, and the CP is 848.9 joules per kilogram Kelvin as well. So what's happening here, we need to determine the work done. That's the first thing that we need to do. But how are we going to determine the work done? They say that we are given the polyprotic cycle process. So that means the polyprotic cycles process, it is basically depending on these four states that we see over here. So this cycle, it has state 1, 2, 3, 4, and then to 1 once more again. Okay, so this is a cycle that will show the polyprotic cycle process. But now, this is what you need to understand. When you calculate the work done, which is W, there are many ways to calculate the work done. But in this case, we're going to calculate the work done using the polyprotic equation, where the polyprotic equation says for expansion, we have P2 V2 subtract P1 V1 divide by 1 subtract N. So basically, this is the equation that we use for polyprotic expansion, right? But you have to understand that the polyprotic expansion, it has different conditions. For an example, we can talk about the polyprotic expansion under the isobaric condition. We can talk about the polyprotic expansion. We can talk about the polyprotic process under adiabatic process. We can talk about polyprotic process and isochoric process. You understand? And we can talk about polyprotic process as it is, where we use the index fraction which is greater than 1. So now what we're going to do over here is, here we are provided with the PV diagram, right? The pressure and the volume diagram. So we are also given the table here that actually tells us about the states that are taking place on this graph over there. So now having a look at state 1 to state 2, we can see that the pressure, it is constant, but the volume, it is changing, which tells us that we are talking about the expansion, since, well, the volume, it is increasing. And then we have state 2 to state 3. We're still going to calculate work from 2 to 3, having a look at that both pressure and the volume, they're actually changing. And then what type of polyprotic process is this? We'll have a look at the numerical values that are provided on the table for us. And then from 3 to 4, we can see that the volume, it is constant, but the pressure, it is the one that is changing. Okay, we'll also talk about that. And then from state 4 to state 1, we'll also talk about that. So without wasting time, let us start by determining the first work, which is between state 1 and state 2. So to determine the work done between state 1 to state 2, is this state. So we have to analyze what is the state 1. From state 1 to state 2, like I said, the pressure, it is constant. When the pressure is constant, what process are we referring to? We are talking about the isobaric process, right? Because pressure 1 is the same as pressure 2, which is constant, and together we're going to call them the pressure because they are all the same, right? 1 and 2. And then the other thing that you need to know that is that when we have the isobaric process, we have what you call the polyprotic index, which is denoted by N. So the polyprotic index in this case is going to be 0 when we have the isobaric process. Okay, like I said, I'm not going to dwell too much on the basics. I just want to solve these questions. So the polyprotic index for isobaric process, we're going to have 0 over there. So to calculate work done under this polyprotic cycle, this is the equation that we are going to use. So what we wanted to get was, what is the value of N? Because the pressure is there, the volume, it is there. Okay, so that's the purpose of us understanding or analyzing what type of process, what type of polyprotic process do we have over there. So in this case, we're going to have negative P2 V2 subtract P1 V1 divide by 1 subtract n. Now, in this case, we're going to have negative. Remember, I'm going to factor out my pressure because it is the same, and then I'm going to call both of them P. So I'm taking my P outside of the bracket, then there I'm going to have V2, V1, close my bracket, divide by 1 subtract n. And therefore, what I'm going to do is I'm going to substitute my pressure because we are talking about state 1 to state 2. The pressure, it is the constant throughout, which is 16.07. And then again, be careful, the units that we are given over here are in bars. And therefore, remember the SI units that we normally use because we want to get to our final answer as joules or kilojoules. So the pressure that is given over here, it is in bars. So what we're going to do is, remember, 1 bar correspond with 100 kilopascal, and 1 bar in pascals correspond with 100,000 pascals, right? So that's what we know. So in this case, I want us to convert this pressure in bars to pascals. So what I'm going to do is I have negative, my P over here is going to be 16.07 times 10 to the power of how many zeros do I have? 1, 2, 3, 4, 5, 6. Sorry, 1, 2, 3, 4, 5. So I'm going to have to the power of 5 pascals over there. And therefore, my V2 in this case, again, from state 1 to state 2, our V2 in this case, it's 8 liters. But remember, again, we do not use the liters, but rather we had a technical error over there. My God. Just had the technical error over there. Let me go back to my questions. Right. So let me solve now. I believe we can solve the questions there. All right. I was here. So V2. So our V2 over here, it is given to be 8 liters. So remember, 1 liter correspond, in fact, I want to start with cubic meters. Okay, let me just do this, erase this. We know that 1,000 cubic meters correspond. Oh, I did it wrong. Not like that. I'm lying. We know that so 1 cubic meter is the same as 1,000 liters, right? 1 cubic meters is the same as 1,000 liters. So basically what we want to do is we want to convert our 8 liters into cubic meters, right? So that means we're going to have to divide this 8 by 1,000 so that it can be converted into cubic meters. So what I'm going to do is I'm going to have my V2 here over there, which is this one on state number 2. 8 times 10 to the power of 1, 2, 3. I'll say negative 3 because we have to divide cubic meters, subtract, and then my V1 over there is going to be 6 times 10 to the power of negative 3 cubic meters. Close my bracket, and then divide by 1. Remember, for isobaric bruises, our polyprotic index is going to be 0 over there, and in there we're going to have 0, right? So what I'm going to do is I'm going to have to punch everything on my calculator. So my fraction negative 16.07 times 10 to power positive 5 multiply by 8 times 10 to power negative 3 minus 6 times 10 to power negative 3 divide by it's 1 subtract the 0. Remember, it's the same as 1 divide by 1. And therefore, from state 1 to state 2, from state 1 to state 2, my final answer will be, let me have a look at this calculator. I'm actually going to get, let me see, did I punch this correctly on my calculator? I want to confirm something. Oh, I did plus sign. It's supposed to be minus over here. You can see this doesn't make sense at all. It's supposed to be it's negative here. Ah, I got it. So my answer will be, let's see, negative 33,214 joules, right? Therefore, this will be our answer in joules. Okay, so that's it for work done from state 1 to state 2. And therefore, now we're going to determine work done from state 2 to state number 3, right? In order for us to do that from state 2 to state number 3, let's have a look at this state over here. So we can see that PV, we can see that the pressure, it is changing, as well as the volume, it is changing. So we can also talk about the expansion. But in this case, let's go back to the numerical values that are provided for us on the table. So now we can see that we move from state 1 to state 3. We saw that the volume is actually changing, whereby the volume, it is increasing. And we also see that the pressure, it is also changing. In this case, we can see that the pressure, it is actually decreasing, moving from state 2 to state 3, right? So again, we can see that moving from state 2 to state 3, now we have at state number 3, we have the polyprotic index, which is now the final ending. So for the fact that we have the polyprotic index, that says a lot. And then we can see the temperature over there, it is also increasing. Now, for the fact that we have the polyprotic index, so that means here, we are not talking about the isobaric. Sorry about that. We are not talking about the isobaric. We are not talking about the isochoric, but we are talking about the polyprotic work for this polyprotic process. So to determine the polyprotic work, we're going to have negative P2, it's P2 V2 subtract P1 V1 divide by 1 subtract N. So for polyprotic index over here, it's provided, which is greater than 1 to be 1,112. Okay. So what you're gonna do is we're gonna have to substitute over here. So now pressure 2 in this case, let's see. Okay, in fact, let me use the state values. Okay, here we have P3, V3, then that's the final, and then the initial. And then the initial, there we're gonna have P2, V2. So P2 in this case, the pressure number 2 in bars, but remember we want the pascals. So it's gonna be, here we're gonna have 5,8 times 10 to the power 5 in pascals. And therefore V3 in this case, it's gonna be 5,8. But do not forget, it's going to be 5,8 times 10 to power negative 3, right? Subtract P2. P2 in this case, it's 16,07 times 10 to the power 5. And therefore, our V2 in this case is going to be 8. Did I do, oh, here I did it wrong. It's supposed to be V3, not, I repeated this twice. So here it's supposed to be, let me see, it's supposed to be V3. So V3 is 20. So we have 20 times 10 to the power of negative 3. Let me confirm the P2 is this one, that. V2 is that one. And then the P3, V3, and then the P2 is this one and that one. So there we have this, and then there we're going to have 8 times 10 to the power of negative 3, close my bracket, divide by 1, subtract our polyprotic index. It is provided to be this number over here, which is 1.112. Therefore, when I punch everything on my calculator, let me do it quick on my calculator. I hope we are also doing the same. So we have 5,8 times 10 to the power 5 multiplied by 20 times 10 to the power of negative 3 subtract 16.07 times 10 to the power 5, 8 times 10 to power negative 3, close my bracket, divide by 1, subtract 1,112. So let's see here, how much do we get? And then my final answer in this case, in joules, I get negative 1,214,285. I'm going to say 2 decimal places, 29 joules. So Basically, this is the polyprotic work that I get at this point in time, okay, following all of the procedures. That will be from 2 to 3. Now we're going to move from state 3 to state 4, right? So now to move from state 3 to state 4, we're going to determine work done from state 3 to state 4. Again, here we have the PV diagram. So now let's go analyze the states from 3 to 4. What is changing? It is the pressure, right? The pressure, it is changing. But what about the volume? We can see that the volume, it is constant. So when we have the constant volume or volume that is not changing, we are actually talking about the isochoric process, okay? We are talking about the isochoric process. And when we have the isochoric process, the polyprotic index in this case, okay, when we have the isochoric process, the polyprotic index in this case is going to be up to infinity because we have a closed system and then there is no work that is actually done, okay, because no volume changes in here. So meaning our polyprotic index, we're going to say it is to infinity, right? So if you want to prove this, it's fine. Actually, work done is going to be 0. Here we're going to have 0 joules. But if you want to prove this using your calculations, let us do it quick. So that means we're going to say here we have P2. Okay, let me use, because remember we are moving from state 3 to state 4. 3 to 4. P2, it's going to be P, the final one is going to be for P4. V4 subtract the initial one is P3 V3 divide by 1 subtract N. So our N, it is to infinity, okay? So without even me substituting over here, look, you can substitute, okay? I just want to show you something. Without me substituting here, at the bottom, I'm going to have 1 subtract infinity. So 1 subtract infinity, it is still going to give us everything here at the top over infinity. And we know that everything on top divided by infinity, mathematically, we know that 1 over infinity, it approaches 0, which is true because when you put this on your calculator, you can start by 100, another 0, add another 0, add another 0, add another 0. You're going to see the number that you're going to get. It will automatically approach 0 because you're going to have many zeros to show that this number, it is actually leaning towards 0. So infinity is a big number. So that's what I'm saying. The more you increase your zeros, you will see that your number will continuously approach infinity. It will approach 0. Okay. So in this case, so meaning the whole expression, the whole fraction expression will automatically give us 0 joules. So that's what I'm saying to you from state 3 to state 4. Have isochoric, the polyprotic index is going to be infinity. And when it's that the case, therefore, there will be no work done in this system at all. Okay. So that's how we go about for this expansion, because there is no expansion. Volume is not changing. It's no expansion at all. So it's 0. Okay. All right. So now, lastly, we're going to move from state 4 to state 1. Remember, you have PV, the volume is decreasing, number 1, right? This is compression. And the pressure, it is actually increasing. The pressure, it is actually increasing. The pressure is getting high while the volume is decreasing. So in this case, what type of process are we actually having from state 4 to state 1? The volume is decreasing, the pressure is increasing, no polyprotic index, and the temperature, it is also increasing. Since while the pressure is increasing, the temperature, it is also increasing. So in this case, we're going to have adiabatic process. Okay, I understand that we have the change in temperature, but adiabatic process doesn't actually mean that. Adiabatic process, it says that there is no heat that is removed, nor heat that is added into system. But one would say we are adding heat because the temperature is increasing. No, for the fact that the pressure it is increasing, meaning the pressure it is lowering the temperature. When the temperature is going up, the pressure is lowering the temperature to avoid the loss of heat and to avoid the gain of heat. So that means in this case, for the fact that the pressure is increasing and the temperature is increasing, when the pressure increases, the temp try to stabilize the temperature by lowering it. So there will be no loss of heat, or there will be no addition of heat at all. So in this case, when we talk about the polyprotic process, but under what condition? Under adiabatic process, we're still going to use the same equation, right? Work done from state number 4 to state number 1. We have P at our final state is number 1, right? P1 V1 subtract P4 V4 divide by 1 subtract n. But here we're going to be a little bit careful, right? Under adiabatic process, our n will actually be represented by a Greek symbol we call lambda. So in this case, how to determine lambda? We're going to use our specific heats. So we're going to use the specific heat at constant volume, specific heat at constant pressure as well. So to determine lambda, we're going to say here we have Cp over Cv. That's how we're going to determine it, okay? So let us determine our lambda. So I will get rid of this n over here as much as we are used to it because we are talking about the polyprotic index. I'm just going to put my lambda over there. So to determine my lambda, I'm going to say my Cp over my Cv. And it is dimensionless because the units are going to cancel each other out. So my CP in this case, I have 849.9 divided by 735. And then when I punch this on my calculator, I have 849.9 divided by 735. And then how much do I get? To two decimal places, I get 1,17. This is what I get. Then now let us go determine the work then. We have negative. So P1 at this point in time, it's 16.07 times 10 to the power 5. And then my V1 in this case, which is the final state, it's going to be 6 times 10 to the power of negative 3 cubic meters. Subtract my P4 in this case, it's going to be 4 times 10 to power positive 5, close my bracket. And my volume there is going to be 20 times 10 to power negative 3, close my bracket, divide by 1 minus my lambda, it's going to be 1,17. So let's see how much do we get here. So we have 16.07 times 10 to power 5 multiply by 6 times 10 to power negative 3, subtract 4 times 10 to power 5, multiply by, let me see, what's that, 20 times 10 to power negative 3, divide by 1, subtract 1,17. And therefore now here, our answer, we get the positive value. In this case, let me see how much is it. I get, let me check something first here. Okay, here what I get is, okay, I think I made a mistake here. I was supposed to substitute 8, okay, because I'm looking at this. I was supposed to do 8 over there, but it's just a minor mistake. But if our CP was 9 over there, this is what we'll get on my calculator. I get my 9658,82 joules. And you see, our work is positive because this is compression, because the volume, it is now decreasing, hence why we're getting this. So this is work compression, okay? So that's what is basically happening, okay? So yeah. and then that's it.